Hello, it's Dr. Mears. Today we are going to be looking at rational graphs and their expressions. A rational expression consists of a polynomial divided by a non-zero polynomial. What does that look like? Here's some examples. 3/4, that's a rational expression. Or x divided by y, another rational expression. Or we can start getting a little bit more complicated, 9 divided by a plus b, or x squared plus 8x plus 7 divided by 3x plus 21. So I'm thinking you're starting to understand that a rational expression definitely consists of division. Let's look at a graph of a rational function, and this is called a parent function. This is where all rational functions start when we graph them. Then they can just get more complicated, like we see up here, 8 for x squared plus 8x plus 7 divided by 3x plus 21. But this is where they all start. They all start at f of x equals 1 over x. And that graph looks like this. And as you can see, this graph, if we look at the x-axis, if we go from left to right and we just look at this curve, it comes all the way down and it gets really close to the x-axis, but it's never going to make it. It also gets really close to the y-axis, which is also our f of x axis. That does not look like an f. I'm so sorry. So y is the same thing as saying f of x. F of x is just a function of x. But we see it gets really close and it's not going to cross this axis. Same with this curve down here. It gets really close to that y-axis and it gets really close to that x-axis, but it's never actually going to cross, which means it has some restrictions. And the restrictions that we're going to talk about when we look at graphs are going to be restrictions on the domain. And when we talk about domain, I'm talking about the x values. And so we see here, it's getting really close to 0. So I'm thinking that the restriction on this graph is that it's never going to be crossing the 0 point, or even this line, y equals 0 and x equals 0, which is this line. So there are some restrictions. Now, why 0? Let's look down here. Notice the domain x values will never include 0. This is called a restriction on the domain. Why? Because if we have f of x equals 1 over x, and let's say we substitute in 0 for x, guess what happens? I don't like how I wrote that, but guess what happens? 1 is in the denominator. And if we try to divide that out on our calculator, if we try to do 1 divided by 0, it's going to be an error. We cannot divide a number by 0. That's because we can't even find a number to multiply by 0 to get back to 1. So anytime that you're in the denominator, you are undefined. And that's why there's restriction, because 0 cannot be in the denominator. I'm going to run out of room. There we go. 0 cannot be in the denominator. So that's what sets up our restrictions. So knowing that, let's look at a couple other different types of rational graphs and look to see what their restrictions are and how we can find them. Okay, looking at another graph here, and I'm going to try to make this a little lighter for you guys. I feel like it got dark in here. Let's look at this other graph. F of x equals x squared plus 5x divided by 2x plus 5. Another rational graph, rational function here. And notice these curves. And these curves, this curve actually crosses at 0. This is 0, this is 1, this -1, -2, -3, -4. But I feel like there is some almost imaginary line here, almost some point. You see that? Where it does get close, but it's never going to cross at both parts. So there is some value on the x where it will never cross. It's difficult to say, though, when you have a graph like this, where the restriction on the domain would be. And so we're going to use what we did before, our information that we know before, to be able to find this exact restriction on the domain. So it's really difficult to pinpoint the restriction. We're going to use a little algebra. The denominator can't be 0, so this is what restricts the domain. So what we're going to do is we're actually going to take the denominator and set it to 0. So here's our denominator. We know this cannot be 0. Can't be 0. So we're going to set it to 0 and see what happens. So if we took 2x plus 5, that's our denominator, we're going to set it equal to 0. And we're just going to do a little algebra two-step equation. Subtract 5, 2x equals negative 5. Divide by 2, x equals negative 5 over 2. And if you would like, you could call that negative 2.5. So if the denominator was 0, our x value would be 2.5. But we're going to see that the restriction is going to be, it can't be 2.5. That's going to be the restriction. It won't cross there because we can't be equal to 0. Okay, so let's go back up to see where that is in the graph. So if we go back up here, here's negative 2. You might not be able to see that very well. That's negative 2. And then this is negative 3. So this is negative 3. This is negative 2. And guess what? This is negative 2.5. And so that's our restriction. So our graph will never cross this imaginary line right here. So it restricts our domain. It will never come in contact with negative 2.5. And so all we did is we just took the denominator. We know it can't be 0, so we set it equal to 0 to see what it can't be, and that's our restriction on the domain, which is our x value. Okay, let's try one more, just to see, because these graphs are getting crazy. So let's look to see if we get a little bit more complicated what's going to happen. Okay, wow, look at this one. Okay, one more. So we're going to find the restriction on the domain of f of x equals x plus 4 divided by the quantity x squared minus 3x minus 10. And so this is what the actual graph looks like. And if you notice, I'm saying actually a lot, sorry. I'm getting excited. We're going to have two restrictions. We're going to have one right here, as you see, it's coming close to kind of this imaginary line right here. And we're going to have one somewhere over here. I'm just taking a guess. I'm thinking it's going to be around there. So I'm guessing by the looks of this, sorry about the numbers being so small, but this is negative 2 and this is 5. So I'm thinking that our restriction on our domain is that it's never going to cross this imaginary line here, this imaginary line here. But we'll see. So let's find out if those are our x values that it can't be. So we know this can't be 0. So what we're going to do is we're going to write this down. X squared minus 3x minus 10. We know it can't be 0, so let's find out what happens when it is 0. Let's find our x values. And this is one of the reasons why I had you factor and why we took our time with factoring is because you are going to have to factor these. So when we factor these, we have to find what multiplies to give you negative 10 and adds to give you negative 3. And that's going to be negative 5 and negative 2. Nope, negative 5 and positive 2. Negative 5 times positive 2 gives you a negative 10. Negative 5 plus 2 gives you a negative 3. And so we had to factor it. So number 1, we set to 0. Number 2, we factored. And number 3, we're going to set each factor to 0. Okay, so we're going to split these up just like we did before. Again, this is why we took the time to factor it and then to solve for 0. So if you remember when we were finding what x is, this is the reason why we want to find what x is, so it can help us to say where this graph will not cross. So we're going to do some algebra, plus 5, so x equals 5, minus 2, so x equals negative 2. We want restrictions. So number 4, so this can't be negative 2 and this can't be 5. So these are our restrictions. And let's just go up to see if we got it right. So can't be positive 5. And if you look up here, I took a pretty good guess. I thought pretty sure it was around 5, and that's right. So x is never going to go through 5. There's this imaginary line here. It's never going to cross. And x is never going to go through negative 2. And if you're wondering what this imaginary line is called, it's an asymptote. So that's what it's called, an asymptote here. That's an asymptote, and this one is too. I'm not going to be referring back to them as asymptotes. I am going to be referring back to them as a restriction on the domain, and we are going to write it in this manner. So that's where we're going to focus on, and so that's what you have to know. Okay, so rational graph, we had a couple restrictions. We saw x equals -2 and x equals 5. We see the picture where we can actually understand. There's where I'm saying actually again. It must be Friday afternoon. And so here are our steps. Set equal to 0, and that's the denominator. Set the denominator equal to 0, factor it, set each factor to equal to 0, and then you have restrictions. That's where it can't be. Okay. So that was graphing. Let's move on to looking at simplifying. So next we're going to be simplifying. Why do we want to simplify? Because it can be helpful when looking for those restrictions. And this is very similar to when you reduce fractions. And that's where I'm going to start. I'm going to start with number 1. We're just going to reduce the fraction 15 over 40. And we are going to think about a number that we can divide 15 and 40 by. And you're right, we can divide 15 by 5, and we can divide 40 by 5. And we're going to see 5 times 3 gives us 15, and 5 times 8 gives us 40. So I actually factored this, and this is where we're going to go with the rest of these equations. And so what happens is I can cross this out, and this reduces to 3/8. Some of you, way back in the day when you were learning how to reduce fractions, you would just say, all right, I'm going to divide by 5 and divide by 5, and you get 3/8. That's fine as well, either way. But I wanted to show you that we are going to be separating everything into a multiplication problem, so we are going to be factoring. All right, let's look at number 2, 8x squared divided by 24x. So again, you could do this a couple different ways. I'm going to take the factored version. So I'm going to split all of this up. I'm going to do 8 times x because x squared is x times x. Okay. And 24 is just 24 times x. Can I reduce 8 24ths? Yes, I can. I can divide both by 8. You can even just simply do that. And then I can cross out these x's, and and I have x left. So I can rewrite it as x over 3. Now, if you're like Dr. Mears, I could have easily done that by just reducing 8 24ths to 1/3 and then subtracting 2 minus 1 to get 1. That's absolutely fine, everybody. I am just showing you what happens when we break everything apart to multiplication. That's it. So let's move on because, again, for number 3, we're going to factor it. So we're going to factor number 3, and then we're going to cancel out. Those are going to be our 2 basic things that we're going to do to be able to simplify. Okay, so number 3. First, let's factor. Is there the numerator? Is there a common factor? Hopefully you said yes, I can factor out a 7a. That's my greatest common factor, and I have a plus 3 left. Great. How about 14? Well, we could do 7a times 2. 7 times 2 is 14. And as you can see, the 7a's, I put them on top of each other because we can cancel out. So I get a plus 3 over 2. And so we're going to factor, cancel. That looks like a cancel. C-E-L, cancel out. Okay, let's try this one. Factor. So let's just, what common factor do we have from 6x plus 12? So we're going to factor out a greatest common factor of 6. I have x plus 2 left over. Okay, I'm going to factor out a greatest common factor from 7x plus 14, 7. I have x plus 2 left over. And this is hopefully where you're going to start to see, I know I'm going to have an x plus 2. I'm probably going to be canceling it out. And so you're going to start to see that you have things that you can cancel out in the numerator and denominator. So these are the same, so I can cancel them out, and I'm left with 6/7. That's really nice. I love going from something as complicated as 6x plus 12 divided by 7x plus 14, right down to 6/7. That is very simple, and that's what we mean by simplifying. Let's go to number 5. I only have a couple more left. Number 5, again, I'm going to simplify. Nope, we are going to simplify, yes, but to simplify, we are going to factor. So just that top, hopefully you are remembering, wait a minute, we factored this. This is the difference. So this is x plus 1 times x minus 1. So this is the reason why we took some time with factoring to remember some of these. Okay, and then in the denominator, we have x squared plus 3x plus 2. So let's set this up. So it multiplies to 2 and adds to 3. And hopefully you said plus 2 and plus 1. 2 times 1 is 2. 2 plus 1 is 3. And do you see something common? I didn't put it on top of each other because they don't need to necessarily be one on top of each other. Just one has to be in the numerator, out, and one has to be in the denominator for you to cross them out. And then you just rewrite what's left. And that's it. You simplified. That's the whole entire process. Okay, let's do number 6. I have number 6 and then I have a number 7 and we're done. All right, number 6, we have 3x squared minus 2x minus 1 divided by x squared minus 3x plus 2. So first we're going to factor to the top. And this might be one because we have an a term that is not 1. This might be one where you want to multiply to negative 3. You had to multiply 3 times 1 is negative 3, and you have to add to negative 2. So if you want to factor like that, where we break this up, 3x squared minus 1, and the numbers that multiply to give you negative 3 are going to be negative 3 and positive 1. Negative 3 plus 1 is negative 2. So negative 3x plus 1x. And then you can group. And this is going to be 3x, x minus 1, and plus 1, x minus 1. And then that's factored by grouping here. And so that's what goes in the numerator. And this could be tedious. I'm not going to give you 45 examples where you have to do all of this. I'm only going to give you a few. We've been practicing this over and over. So I'm just going to give you a couple where you're going to have to do a little bit longer factoring method. Hopefully you can remember some of the shortcuts like the difference here, x plus 1, x minus 1. So, but you do have to be really good at factoring so that you're able to factor and then skip to that simplification part. All right, and then the denominator, we have x squared minus 3x. So what multiplies give you 2 and adds to give you 3. We can just do this method because this is 1 in front. So x and 2 and 1 and minus 2 minus 1. Negative 2 plus negative 1 gets you negative 3. Negative 2 times negative 1 gets you positive 2. And then we look to see what we can cross out. What is in common? So we have x minus 1. Oh, I made a mistake, everybody. I'm so sorry. This should be minus 1. This should be minus 1. Minus 1, minus 1. This should be minus 1. And so I just want to point out that I did make this mistake down here. But when we went here and we were looking to cross something out, we knew it said simplify. So we're pretty sure we're going to have to cross something out. And this was a plus. And I was like, wait, we don't have anything to cross out. That means you might want to check work if you don't have anything to cross out like I did, because we did make a silly mistake. I'm going to do a little check with an S for a silly mistake here. And that did transfer over. But we fixed our silly mistake. And now we're able to cross this out. I'm actually glad we made that silly mistake because we were able to check our work. We were able to find our silly mistake. And then we were able to correct it and see that we have these two are the same, so they cross out. We write down what we have left, 3x plus 1 divided by x minus 2, and we're simplified. And our last example for the day on this Friday afternoon that I'm making the video, we're going to bring it all together. First, we're going to simplify. Then we're going to find the restrictions on the domain. So we have f of x equals x squared minus 4 divided by 2x squared minus 3x minus 2. Again, a little bit longer factoring here, but let's go. So first, let's factor the top. Hopefully you're saying, okay, we know this one. And you're going to be seeing this one a lot. You're going to be seeing the x minus 4 a lot and the x minus 1 a lot. So x plus 2, x minus 2. This one, a is not 1, so we're looking at multiplying to negative 4 and adding to negative 3. I am going to give you the factors. The factors are going to be 2x plus 1 and x minus 2. That's what you get when you factor this. Okay, I didn't do out the whole process. If you need practice being able to factor the denominator or something like the denominator, let me know and we can work together. All right, what do we see that we have in common in the numerator and denominator? Perfect, so we're going to cross that out. So f of x equals x plus 2 over 2x plus 1. So we simplified. Great. And now since we simplified, we can find restrictions on the domain. So we can say, all right, this can't be 0. So 2x plus 1, let's make it 0. Tell me we can't do it, let's do it. Minus 1, 2x equals negative 1, divide by 2. So x equals negative 1/2, but it's a restriction. That means we can't have it equals. So this is my restriction on the domain. And what I'm going to show you now is actually the graph and how this is a restriction. So you see our pieces start coming together. And here below is the graph. That's the graph. And as you can see, here's 0, here's negative 1. And so right in the middle, this is negative 1/2. And you can start to see that asymptote right here, that imaginary line that graph won't cross. So our restriction is going to be negative 1/2. We found that here when we set the denominator equal to 0. The reason we set the denominator equal to 0 was because we simplified, and we were able to simplify because we factored. And so that's one of the reasons why we need to know how to factor, is so that it can help us start to understand graphing, where graphs are restricted and where they're not. I hope this helped. It has been graphing rational expressions, simplifying rational expressions, and a little review of factoring. Thank you.